Hi, good morning or good afternoon for those of you in the other part of the world. My name is Frederic Reverdy, and we're welcome to this new coffee break with Eddyfi. I hope you have your coffee mug. And today we're going to talk about HTHA, high temperature hydrogen attack inspection. All right, so what is HTHA? So HTHA is a form of damage that mostly occur in carbon steel. It can happen in other type of steels that are submitted to high pressure with hydrogen environments and high temperatures. So what happens essentially is the hydrogen, being the smallest atom diffused through the steel, is going to react with carbon to create methane, so CH4, which cannot diffuse into the steel anymore. So you're going to create bubbles around the grain, and these bubbles are going to coalesce and to create microfissures. You can actually see some microfissures right here around the grain. You can see the scale of about 20 micron. And eventually, if the pressure keeps going on, and if there is internal stress, you can create macro cracks, which can really impact the structure of the asset. We all remember what happened in Washington State, unfortunately, in 2010. So the damage can be ranked into different stages, which are essentially based on the size of the defects. So initially, as I said, you start with microbubbles around the grain, about less than 50 micron, which is pretty much impossible to detect with UT. Then you go to stage two, microfissures between 50 and 100 micron. And you can kind of see the scale right here, again, 50 micron. Then you have macrofissures, so greater than 100 micron, and eventually you go all the way down to a macro crack. You can see right here. But at any point, you can have several of these stages coexisting at the same time. So just because you have a macro crack doesn't mean that around it you don't have macrofissures or microfissures that can create problems detecting. And I want to thank some of the Lavender, like for some of the pictures, and other people on the internet. So before, there were like several methods, NDT methods, that were used on the API 941 for the detection of HTHA. So you have a list right here: velocity ratio, attenuation, some spectral analysis, and some ultrasonic backscattering. And a combination of those techniques kind of gave some interesting results, but unfortunately, sometimes they were unreliable or they had some repeatability issue and very dependent on the operator. That's why the API was revised to include more modern technique. The first two are TOFT, time of flight diffraction, and TULA, so TOFT ultra low angles, which are essentially some screening methods. They are being used because they are pretty fast to detect potential HTHA. So we are all familiar with TOFT. This is a very well-established technique that's used all the time for well inspection. This is highly sensitive, and it goes really fast. So for HTHA, if you select your probe parameters correctly, so essentially your diameter and your frequency, and because we're looking at small defects, we are going to be using 7.5 to 10 megahertz, you can really optimize your inspection to inspect the full volume of the weld, heat affected zone, and some of the base material. And you have this very typical TOF data with the lateral wave, the backward echo, and potential mode conversion. But what's interesting for us here is what's happening in between, essentially right here. All these kind of scatters is indicative of HTHA. And of course, you need a trained eye to start recognizing that you have HTHA. Another method that can be used for fast inspection is TULA. As I said, is TOFT ultra low angle. So this is essentially a TRL configuration, transmit receive, where you have an emitter and a receiver at pretty high frequency, about 10 megahertz. And you have different probes with different roof angles, so you can actually inspect different thicknesses. For this particular example, you can see here the beam calculated in ultravision, and you can see here that you are going to be sensitive to that particular region. So being a conventional probe, you need to scan it. So you can do it, have like a live scan, or you can record the data using an encoder, 1D or 2D, such as a sweeper, for example, from Eddyfi. And that's the type of results you are getting. So this is the back wall, and the HTHA data is right here. You can see also on the A scan. So this one is a pretty advanced, probably like stage 3 and 4. But around it, as we talked about earlier, you are going to have some stage 2 and stage 1, which we are probably not going to be sensitive. Tula is interesting because if we are looking at very thick component, let's say 3 or 4 inches, if you use soft, you're going to have a very large PCS. Here, because the two probes are close to each other, you don't have this large PCS issue. So that's pretty good for thick material. So these two techniques are used for fast screening. But you usually need to confirm the presence of HTHA with other techniques, such as phased array, so PAUT, and total focusing method. So they are both part of the new API revision to confirm the presence of HTHA and potentially characterize the HTHA. So we are all familiar with phased array. So the big advantage of phased array is that it provides you a real-time image of a cross-section of your sample on top of having the A-scan to look at amplitude or other things. So by scanning this phased array, you can have a full volumetric image of your sample. You can record the data and you can compare to further inspection, which is pretty interesting for HTHA because you can have an evolution of the HTHA over time, and you want to be able to compare, to previous inspection. So we have, if you can go on our website here, we have the catalog with all the phased array probes and TOF probes available because, as you know, we acquired Sensor Networks last year. And you can see here some images like a typical A32. I will use an A32 10 megahertz for HTHA, for example. So when you use phased array for HTHA, so first we did our screening with Tula and Toft. So Toft is going to provide you with the depth information. It's going to tell you like you have potential HTHA at this depth. But it cannot really locate where the HTHA is going to be in the weld, heat affected zone, or within the volume of the Toft coverage. So that's why PAUT is interesting, because you can then switch to PAUT. You can focus the energy at the depth that was detected by Toft, and you can try to confirm the presence of HTHA. And you can have various scan plans based on the type of component you're inspecting. Obviously, for like a weld inspection, you're going to do the same as a typical weld inspection, except you're going to be focusing in a heat-affected zone because that's where the high stress is going to be, and potentially that's where HTHA is going to be. It can be along the ID, OD, or along the entire heat-affected zone, depending on the weld configuration, if it's a circumferential versus longitudinal weld, if it's a V or double V, and so on. And you can also do some linear scan if the weld is flush, for example. Early stage HTHA, we saw the stages, really small defects. So it's going to be, ultrasound is going to have a very, very, very weak response. So when we switch to PAUT, we have to improve sensitivity as much as we can. And one way to improve sensitivity is to focus the energy at the right location. And the bigger the aperture, it's like a microscope. The bigger the aperture, the smaller the focal beam is going to be, so the higher the sensitivity. So here we are looking at a sample that contains HTHA along the back wall. It's a 1-inch sample, 25 millimeter. So the HTHA is right here. I'm using 16 element, 32 element, and 64 elements, so at the same time, a multi-group configuration. And I'm focusing the energy around 22 millimeter right here. And we can kind of see what's happening as I move the probe on the sample. And you can really see here that the 64 elements is really bringing all this scattering that you can see that on a 16 element, for example, that could be confused with electric noise and would be very hard to call anything here. So the bigger the aperture, the better the sensitivity and the resolution to detect HTHA. Well, so we know that we can increase the aperture to have a better detectability. But we can push the envelope a little bit further because we really want to catch HTHA as early as possible. So, well, we increase resolution in the active plane. Well, we can also increase it in the passive plane. Typically, when we use phased array probes, we have flat elements and they have a natural focus. But we can increase the focus in the passive plane by using a DLA configuration, for example, a dual linear array. And you have here the reference from the probe. So we have designed a probe which is 2 times 64 elements, so 64 emitter, 64 receiver, with a small pitch, so we can have a pretty good steering of the energy. And the fact that we are separating the emission from the reception, so I'm going to fire the emission and receive here, you have this natural convolution of the two beams, and you're going to have a natural focus. And you can see here, that's the emitter, that's the receiver. We have the energy across the passive plane, so we're going to be very sensitive within that region. We have an acoustic barrier between the emitter and receiver. That means that we are going to hide the bang from the front surface. So we're going to have pretty much no dead zone as well. So it's going to be interesting to use it for thinner samples or when we have HTHA going all the way up to the front surface. If we compare that probe to a standard linear array at 10 megahertz, so same frequency, so we supposedly have the same wavelength. You have here a mechanical scan, so this is the mechanical axis. And you can see that the front surface echo that you have with a conventional linear array is gone with a dual linear. This is one of the advantages of TRL configuration, is you get rid of the front surface. Another one is the length of any indication. So as I move my probe and I have very small indication, because HTHA is really small, I'm going to convolute the response of my defect with the size of my beam. So when I have a large elevation, I'm going to have a large response. So this is why in the passive plane, defects appear stretched out. So now if I use the DLA and I have a focus along the passive plane, you can see that the resolution in that plane is reduced. So we have a better resolution for the detection of any indication along the passive plane. And because we have a better resolution, we also improve the signal to noise ratio compared to a standard 10 megahertz probe. So we can do that for L0 inspection with a DLA, for example, but we have another way of improving resolution with linear arrays. We can use focused linear arrays. So I have here 3 references at 5 megahertz, 10 megahertz, and you can see the DF50 is the depth at which we are focusing in the passive plane. But essentially, a focused linear array is just a standard linear array, but the shape of the piezoelectric element, instead of being flat, are going to be curved. And depending on the curvature, you're going to be able to focus the energy at different depths. So that's why we have these 3 different probes. So we have designed this probe with 64 elements, because again, in the active plane, we want to have a large aperture, a pitch small enough so we can have a full steering or as much of a steering of the component for PAUT and TFM applications. It is focused in the passive plane to improve the resolution along that plane with different curvature at different depths. And you can see here an image. We try to make it as small as possible for better accessibility around the wells or other components. And if we compare that probe to a standard, so in this case, that's the 5 megahertz probe using shear wave. You can see here with a new probe compared to here, we have improved the sensitivity. We have a better signal to noise ratio and a better resolution along that plane. So we have these 2 new designs. Of course, you can still use standard phased array at 10 and 7.5 megahertz, but you also have now the choice to increase sensitivity going with these optimized designs. So we have done the fast screening with TOFT and TULA or TULA. We can confirm the presence with phased array. And another technique that we can use is TFM, total focusing method. I just told you that we need to use a larger aperture with phased array to focus the beam to a tighter spot so we have better sensitivity. The problem when you do this is like you have this really nice focus, but then you have a very, very small depth of field. So if the operator is not putting the depth of field at the right location, then it might not be sensitive to other locations where there is HTHA. So the operator has to be very, very careful when using phased array to confirm the presence of HTHA. So one way to go around that is to use TFM. So I'm not going to go into explaining the technique today, but you can go into our website, the Academy, Eddyfi Academy, and there is a small video that is about 30 minutes that explains how TFM works. So that's a good way. But in a nutshell, TFM is just similar at focusing the beam at every pixel of a region of interest. So let's say we have a region of interest composed of pixels. I'm going to use the full aperture of my array, and I'm going to focus the energy at that pixel, that pixel, that pixel, and so on, at every single pixel. So at the end, what you obtain is an image, of course, with the smallest focal beam at every single pixel of the image. So you have the best spatial resolution possible for every single pixel. You're not simply just focused at one depth or one projection like you would with phased array. You'll be focused everywhere. Of course, you can still apply a time-corrected gain, a TCG, to make sure that you have the same amplitude everywhere. You can look at the ISO standard that, about TFM. But also, because we are focused everywhere, you don't have the depth of field issue because each pixel is the result of one dedicated focal law. So you don't have to worry anymore about where to focus the energy. It's going to be focused anywhere, of course, as long as you are in the near field. And the first use of TFM for HTHA was actually from British Petroleum, BP. And you can see here an image of the older Gecko, because the Gecko was the first phased array equipment, portable phased array equipment on the market with real-time TFM. So we introduced TFM a long time ago. And these are some of the results that were obtained by BP. And they wrote a paper back in 2020, so also a good read about assessment of high temperature hydrogen using advanced ultrasonic techniques such as TFM. We were also part of that paper. So just a couple of images. So going back, if you remember that sample that we looked at with Tula, this is the same sample. It's about 90 millimeter thick or 3.5 inches. So we obtain kind of the same image we had before with Tula. You can kind of see this growth of HTHA. If we look at a cross section, so I'm going to be perpendicular to the screen, this is the type of image you can obtain. So you can really see here the cluster of HTHA with some with a stronger response, and on top of it, you can see that a weaker and weaker response. Because again, you can have a stage 3 or stage 4 HTHA, but it's always going to be surrounded by earlier stage as well. And this is probably what you are seeing right here, like some stage 2 HTHA. So you're using like a 10 megahertz with a good aperture, you're going to be able to focus the energy. And you can see here like a top view. You can see the HTHA around here. And this is kind of the beginning right here where it's a little bit weaker. Now going to the Gecko, before that was kind of a topaz image with angle beam this time. So I'm going to use one of the optimized probe with a curvature. You can see here that's a 1-inch sample. You can see here the macrograph taken along the back wall. So this is 50 micron. So we have a stage 2 HTHA sample right here. And we are defining our TFM area using plane wave imaging. So instead of doing a full matrix capture, so firing the elements one by one, here I'm going to fire all my elements. So I'm going to do a sectorial scan with a full 64 elements, and I'm going to do a TFM reconstruction at the same time. So what's the advantage of doing plane wave imaging here? When we fire only one element doesn't send a lot of energy. And when this energy, which is usually divergence, you have a large beam spread, arrives at the HTHA, it's going to be scattered by all the micro cracks and everything. So some of the energy is not going to go back to the probe. And potentially, like, there will be nothing going back to the probe because we didn't send enough energy. So by firing all the elements at the same time with a big punch of energy, we have potentially more chance of getting this energy back to the probe. And also because we fire less than 64 times, we are all going to improve productivity. We're going to have a nice scanning speed, which is going to be like 100 millimeters per second. So you don't have to go very slowly. And in that image, we did a time-corrected gain to make sure that we have the same amplitude across the entire TFM image. And you can see here along the back wall, that's where we have the HTHA. You can really see all this scattering right here. You can see some of the grain because, again, we have a 10 megahertz probe that's focused in the passive plane. We focus in the active plane. So we really start to have very small beam, but you can really see the difference here for this stage 2. And if you look along the mechanical axis, you can really see again the HTHA right here. And on EScan with the TCG, you can see the grain structure right here. And as we go along the back wall, there is this increase in energy due to the scattering of the HTHA, stage 2 HTHA. So TFM on top of PAUT is another method that can help you confirm the presence of the HTHA after doing a fast screening. A new technique, which is not part of API, which is phase coherence imaging, or PCI. And we did a blog on our website about PCI, because again, this is not also, none of the methods are silver bullets. It's more the combination of them that makes the detectability of HTHA possible. So we did a blog about the pros and cons of the technique, but HTHA is the perfect application for phase coherence imaging. If there's one application that's good for PCI, this is HTHA. So essentially, again, I'm not going to explain PCI today, but PCI is the same as TFM. It's calculated exactly the same way. The only difference is that we are looking at phase information instead of the amplitude information. And by doing this, we're going to be very sensitive to small indications that tend to send energy everywhere. And HTHA is essentially that. It is a cluster of microcracks in everywhere and oriented in all directions, so that basically are going to send energy everywhere. So here you have two PCI images. The left one was done from a full matrix capture acquisition, so firing the element one by one, and the other one is from a plane wave imaging acquisition. So again, I'm doing a cycle scan with my all my elements, and I did that as a multi-group, so I can be sure that I'm at the same location. Uh, the PCI usually comes with a dedicated nonlinear palette. So you can see here the high amplitude, so it's not amplitude, but the high values for PCI are usually in the pinkish red color. And if you look at the image right here, and probably if you are trained and you know what you're looking for, you can kind of see this gray right here, right? And maybe we are going to call it HTHA. But I will say that this is probably difficult to call HTHA here. That's probably, for me, would be more like electric noise. And so why don't we have more signal? Again, when we do PCI from a full matrix capture, we fire the elements one by one, so we don't send a lot of energy. And if there is a lot of clustering, most of the energy is being basically like diffracted, diffused across the HTHA, and nothing comes back. And you have a zero signal to noise ratio from all the signals of the FMC, so you cannot extract a phase. So you need to send more energy. So we use the same probe, but we use plane wave imaging for the excitation. So we fire all the elements. So we send this plane wave in different directions. They are being scattered by the HTHA, but some of the energy comes back. And you can see that I am on the same scale right here. I'm not compressing my scale. And I think it's pretty straightforward to see that there is a difference between these two images. And you can really see here this part of the sample. This is a top view, by the way, compared to this one, has some HTHA. And you can kind of see the HTHA right here. So by combining PCI with the dedicated probes I showed you before and plane wave imaging, you can increase your chances of detecting HTHA. So I think that PCI is an interesting new method that can be used for HTHA. All right. So in conclusion, so HTHA is kind of a different animal here for NDT, especially for ultrasound. So detecting HTHA relies on several things. First, you have to know the life of your asset. You have to know the type of stress it's under, the history of pressure and stress, the type of material, if it's a carbon steel, how much chromium there is in it. So to know the susceptibility of having HTHA. Then you need to be trained on the different NDT techniques. I mean, like any NDT, you need to be trained, but you need to have access to samples with real HTHA and to have your brain being trained on recognizing tough data on HTHA. So our friends at Lavender, and thanks Tim Armin for the discussion we had a couple of weeks ago, uh, basically have a lot of samples and they can show you the different techniques on it. And of course, you need to have an efficient and robust inspection strategy that combine all these techniques that are part of API, not PCI, that's why it's in italic, and have an equipment that can provide you all these techniques. So at Eddyfi, we have the Gecko, which you have here on the left, and the Topaz 64. They are phased array units, basically that provide you with TOF, TULA, PUT, TFM, and also live PCI. And you can combine some of these techniques. So if you want to do TFM and PCI at the same time, that's something you can do. You need to have the right probes. So Eddyfi has a lot of phased array probes, standard phased array probes, and also optimized phased array probes are presented today, and some TOF probes. And you can combine that to 1D or 2D scanners. So here I have an image of our sweeper, which is a 2D scanner. So the wheels, you can see here, are encoded into that direction. And there is another one underneath to encode into the other direction. So you can really do like a raster scan, and you can see here the DLA probe, so the 2 times 64 elements being used for the inspection of HTHA. All right. Thank you for your time. I hope you enjoy it. And I'm ready to take some questions. All right. So, hi, Carlos. Have I attempted to validate TFM with FFT images? Not in depth. I try to do it a little bit. Uh, I didn't see a lot of correlation between TFM and FFT, and I think the difficulty here is when you do Fourier transform, you need to make sure that you have very nice surface condition and everything, and that's probably why some of the spectral analysis methods in the old API were not reliable. But I don't have a lot of experience with it, to be honest. Yeah, so that's all. Can you, hey Victoria, can you distinguish between HTHA and other defects? So that's very often a question that comes back because, as we become very sensitive to these small defects, we also become sensitive to grain, noise, and to other things. So that's why when I conclude and say like you need to know your asset is, for example, let's say you have some porosities and with the laminations that are going to appear horizontal. So when you fire at 0 degrees, you're going to see them very nicely. And you can confuse them with HTHA. But because they are being laminated and become horizontal, if you combine a L0 inspection with a shear, the shear is going to send the energy this way, and you're not going to see them. So you need to combine different inspection strategies or different technique to make sure that you're not confusing HTHA with other defects. As far as a bad steel, then kind of the same thing, right? If you have a steel that has a lot of grain structure and you put your probe right on top of it, you can call for HTHA. So you really you really need to know the asset you're inspecting before you make a call. So that's one of the difficulties with HTHA. What about PWI, PCI, TT mode for detection and validation as well? Well, I would say like now looking at the speed of PWI, since we can go pretty fast and we can do PCI and TFM at the same time using a TT mode, you could use it if you want for detection and validation at the same time. I think it really depends on you. I think like the training, for example, at Lavender is teaching you how to use different techniques to do it. But I think it's up to you if you feel like you have a technique that basically can do the detection and the validation at the same time because it is fast enough. And you're right, with plane wave imaging, we are reaching speed that are good enough, so that can be used. I would still, because of the difficulty, and going back to the previous question, if you only do like shear, uh, I guess you're not going to miss a lot of defects. So yeah, I guess that's a way to look at it. PWI and doing TFM and PCI at the same time. Yeah. All right. Thank you. And you have here my email address in case you have any questions. Please fire at will. And I will see you in another coffee break. Thanks for your time and good coffee. Take care, guys. Bye.